The theme for today is topological sort, which comes in handy for course scheduling and other dependency-related problems. Without further ado, let's have a look at a couple of problems and see how a variation of that theme can be applied to solving those problems. First up is a problem called course scheduling. 207 course schedule medium. There are a total of num courses you have to take, labeled from 0 until num courses minus 1. Some courses may have prerequisites. For example, to take course 0, you have to first take course 1, which is expressed as a pair, 0, 1. Given the total number of courses and a list of prerequisite pairs, which means there's only like one dependency edge, so to say, that is being listed. It is possible for you to finish the course, yes or no. Specifically to finish all courses, yes or no. Example 1, num courses equals 2, prerequisites 1, 0. True, there are a total of 2 courses to take. To take course 1, you should have finished course 0, so it is possible. Num courses in example 2, 2 prerequisites, 1 requires 0 and 0 requires 1, so now we got like a dependency cycle, and it is false because there are a total of 2 courses to take, and you end up being in an infinite loop in having to finish each other's courses first before taking the other one. It comes with a couple of constraints. The input prerequisites is a graph represented by a list of edges. So those pairs are edges, not adjacency matrices. Read more about how a graph is represented, and they have some links here. You may assume that there are no duplicate edges in the input prerequisites, and the total number of num courses will not exceed 10 to the power of 5. Next up is sort items by groups respecting dependencies, hard. Number 1203. There are n items, each belonging to 0 or 1 of m groups, where group I is the group that the ith item belongs to and is equal to -1 if the ith item belongs to no group. The items and the groups are 0 indexed. A group can have no item belonging to it. Return a sorted list of the items such that the items that belong to the same group are next to each other in the sorted list. There are some relations between these items where before items I is a list containing all the items that should come before ith item in the sorted array. Return any solution if there is more than one solution, and return an empty list if there is no solution. So then we go through a couple of examples where certain prerequisites need to be considered. So we get like n items, m equals 2, and then we get like this group listing, -1, -1, 1, 0, 0, 1, 0, -1 for each of those items. And then the before items are basically none for 0, 6 for item 1, 5 for item 2, 6 for item 3, 3, 6 for item 4, and then no more prerequisites for 5, 6, and 7. And then the output ordering would be, since 6 appears here a lot, 6 should be handled first. 3 appears here, so 3 should be handled first. 4, 1, 5, 2, 0, 7. And then we get like another listing where it's impossible. This time we didn't have the table drawing, but it's basically, it goes the same order with 8 items, m equals 2. And then we got like our group being -1, -1, 1, 0, 0, 1, 0, -1. And the before items are empty, 6, 5, 6, 3, empty, 4, empty, and the output is empty because this is the same as example 1, except that 4 needs to be before 6. And we figured out from the previous example that 6 needs to be basically the first item to be handled, and therefore there's like a loop in the dependency graph to be found out. And once we found that one, we can return that solution. Third example is 2010 course schedule 2, medium. there are a total of n courses you have to take labeled from 0 to n minus 1. Some courses may have prerequisites. For example, to take course 0, you have to first take course number 1, which is expressed as a pair 0, 1. That all sounds familiar from course schedule 1. Given the total number of courses and a list of prerequisite pairs, return the ordering of courses you should take to finish all courses. There may be multiple correct orders. You need to return one of them. If it's impossible to finish all courses, return an empty array. So we got 2 and as the number of courses you have to take. And then you get this prerequisite of 1, 0. Output is first 0, then 1, because you have to take course 1 before you can take course 0. And then we got 4, 1, 0, 2, 0, 3, 1, 3, 2. Output is 0, 1, 2, 3 or 0, 2, 1, 3 with the explanation. There are a total of 4 courses to take. To take course 3, you should have finished both courses 1 and 3, which means you have to first take 1 and 3 regardless of the order before number 1 and 2 before number 3. And 1 and 2 both should be taken after course 0. So that means like we've got 0 and 3 pretty much fixed, and then it's only about how to put the courses 1 and 2 in there. Note, the input prerequisites is a graph represented by a list of edges, not adjacency matrices. That sounds familiar. You may assume that there are no duplicate edges in the input prerequisites. So much for that. And with that in mind, let's have a look at the underlying theme, which is topological sorting, as I introduced. The best website to have a look at among multiple websites, because this is like a sort of well understood path that has been taught at undergraduate level in most computer science classes. So it's a well understood topic, but I think Geeks for Geeks this time pretty much nailed it. For those who don't know the website, Geeks for Geeks is a computer science portal for geeks. So it's topological sorting, and it's basically finding out the dependencies in a directed acyclic graph. So we know like from one node to another there's a directed edge, and that doesn't mean that the edge goes in the other way too. So there's always like an arrow to it. And the way to tackle it, as explained here in greater detail, is basically to do a depth-first search with the understanding you can start from a vertex. That could be, so far, could be anyone. And then you go through all your vertices in your graph using a depth-first search order up until you don't have any vertices anymore. And then you put them in a temporary stack. You don't print the vertex immediately, you just put them all in a stack and then call topological sort up until you have finished calling topological on all vertices, meanwhile keeping track of which vertices you have visited. And then at the end, you print the stack. And that would basically give you the ordering. Because the item on top of the stack is the item most other items depended upon. And then you go backwards, and then the item at the bottom of the stack is the least dependent upon item. With the note, a vertex is pushed to a stack only when all of its adjacent vertices are already in stack. So that's that recursive fashion where you first continue to call before you do an operation on your current node. You just like go all the way deep, and then once you hit rock bottom, you kind of add to the stack, and then you go backwards. And then the key thing is that if you encounter a loop where you have visited already, you should flag this or kind of give the output saying that you have encountered a stack where you visited already, but you also have a dependency upon. Again, since it's Geeks for Geeks, it comes with like a nice implementation in different popular coding languages and with some test cases as well. So that's all pretty neat. And with that in mind, let's go back to the problems and see how that theme was varied upon in order to solve those problems. First up is course schedule. Topological sort is used here to find out if it is possible or not possible to finish all the courses, right? And the key thing here is basically you do your topological sorting as outlined already in Geeks for Geeks description. Right here you have that recursive call that's paramount and prior to everything else happening. Meanwhile, you also need to make sure that you are flagging where you have been already, right? So you flag that you visited the node, and you make sure, here's the key part, that you flag it for cycle detection. So you go through and you call yourself, and then two items are key here. First, you check if I haven't visited yet, then keep calling. Else, if I have visited that neighbor already, check if there's a dependency cycle. So if that neighbor has been visited already, and that neighbor is already basically has a cycle on myself, or like has a dependency that leads back to myself, then I will flag the cycle as true and return. And cycle true is then it's like a member bool variable that we then basically just query at the end and say if there's a cycle, then we can't find a way to schedule all our courses to finish. Otherwise, if no cycle exists, then we can finish all our courses without needing to actually give a detailed explanation which courses we visited in which order. So that's just like a given. And prior to that, we make sure that our prerequisites are neatly pushed into a list of adjacencies, which we then use for our topological sort and for our visiting. Next up, sort items by groups respecting dependencies, and that's the topological sorts, very nicely commented upon in most of those lines here in our code, and with some nice data structures to just keep track of all our items and how they are depending on each other and in which group they are belonging to. So here, let's have a quick look on where the dependency graph computation actually takes count. We do it here with the topological sort. Here they actually use it with a queue-based approach, which is a bit of a stretch, but it is possible to do. And they basically do it by just visiting and then making sure that once you have a circle within the queue, you immediately return an empty set and saying it's not possible. Otherwise, you push your items back into the queue and continue to do your computation. And up here, this part of the code basically does the establishing of the adjacencies that are necessary for our topological sort. So third item today to look at is the course schedule number 2. Kind of similar to the first one. Comes again with a visited, with a adjacency list and a Boolean for cycle. It comes with its own depth-first search approach to do the topological sorting, so to say, and to detect the circles. Key, again, as we saw before already, as soon as we call, we flag our visited, and we flag our potential circle or cycle candidates in that additional vector, vector of booleans, and then we just continue to call ourselves if and only if we have not visited that neighbor. Otherwise, we just like infinitely call ourselves. But if we have visited the neighbor, we check if there's not like a cycle situation going on already. If there's a cycle situation going on, we flag it and return. Otherwise, we have made it all the way up until here, and we are actually able to push our results for the ordering. And then we push that node into our result vector, where we have our final ordering for the course schedule. And find order is the main function that calls the other function. So we go in here, have our number of courses with all the adjacencies flagged as prerequisites. And while we are doing that, we set up in a for loop, we set all those adjacencies in an adjacency list. And then for all the number of courses, we call the entry depth first search, such as if we don't have like one connected graph, but maybe have like some sort of forest situation going on of disconnected graphs, such that we can still continue to call back in and make our final result vector. And then the key thing again is we've touched on this a little earlier in the Geeks for Geeks website to print in the reverse order, right? So if we have a stack, then this is no problem because we have it on the most dependent upon item is on top of the stack, and then the least dependent upon item is in the bottom of the stack. So here, since we have a vector situation going on, we have to reverse that vector in order to get the correct ordering, to have the most dependent upon item printed out at the beginning, the least dependent upon item printed out at the end. And that's all to it for topological sorting. We have seen the theme of topological sorting and seen 3 variations of it to tackle problems and scenarios where topological sorting comes in handy to solve it.